This is part 3 of a discussion of the pulmonary system, chapter 22 of our Human Anatomy and Physiology, part 2. Last time, if you're just joining us, we talked about the lower respiratory system and the respiratory membrane, that membrane across which the oxygen and CO2 must diffuse during respiratory function. And now we're going to talk about the mechanics of ventilation. How do we actually get the air in and out of the respiratory system? And then we'll talk about a clinical strategy for assessing that process, being able to actually measure the air being inspired and expired, and its application to a couple of just very basic broad categories of lung diseases. So in order to really understand how we ventilate, we should look at Boyles Law. And this might seem off-putting for people that don't really have a lot of experience in physics or physiology, but actually it's pretty straightforward. Let me explain what's going on with this formula. If we have some air trapped in a container under pressure, and that means that the massive, the air molecules which have mass have a lot of kinetic energy. They're bouncing off the walls, and as they strike the walls, they exert a force on the walls, an outward force, which is what we mean by pressure. It's the force per unit area on the walls of the container. So they're doing that. If we increase the volume suddenly and don't change the number of air molecules, then the pressure will go down. The number of collisions per second of air molecules will be less because they're more spread out and we have less force and less pressure. So if you take a container of a set amount of gas that increases volume, the pressure goes down. If you take that same container and confine those air molecules in a smaller volume, there's going to be more collisions per unit time and the pressure is going to go up. And that's, we exploit those properties of gas in order to ventilate or breathe. Let's take a look. We're going to make changes in the volume of our thorax or of the lungs, and air is going to flow from high pressure to low pressure into the lungs if we lower the pressure, increasing the volume, and if we decrease the volume, air is going to flow out. Let's take a look at a little cartoon of the lungs as this is happening to just run through the steps of what we're doing here. We start out by contracting for inspiration, that is, for bringing air into the lungs. We start out by contracting some muscles, and at rest just the diaphragm muscle, the dome-shaped muscle we looked at once before, situated underneath the lungs. If we contract that muscle, it's going to flatten out across this space. It's going to increase the thoracic volume. We contract that muscle. The lungs are pulled down along with the diaphragm, right? Because the diaphragm has the parietal pleura attached to it, and then the visceral pleura is attached to those lungs. They have no choice but to expand right along with the thorax. And so the pressure will drop. If we increase the volume, we still have the same amount of air in there. We're going to decrease the pressure. And so now air just passively flows from high pressure outside the body to lower pressure inside the lungs. That's how we inspire air. If we actually are exercising and we want to be a little bit more vigorous about things, we'll use the intercostal muscles to also elevate the rib cage, which will also increase the volume even more. Expiration, how do we get air out of the lungs? Expiration or exhalation. We first relax the diaphragm. If we're breathing at rest, all we do is relax the diaphragm. No extra muscle contractions are needed. All the alveoli are elastic and they are going to recoil, and along with the chest wall, and those elastic recoil forces are going to reduce the volume in the thoracic cavity and in the lungs. Right, the alveoli just want to shrink right down, and if we reduce the volume, we raise the pressure. And if there's a higher pressure inside the thorax than outside, air just flows out from higher to lower pressure. So we create a pressure gradient by first changing the volumes, and then the pressure changes and air flows. Again, we may breathe a little more vigorously than that. So at rest, inspiration occurs by contraction of the diaphragm alone, and at rest, expiration or exhalation occurs simply by relaxing the diaphragm, and elastic recoil is with a force that's used to decrease the volume and air flows out. During exercise, inspiration is assisted by contracting the external intercostal muscles. That raises up the rib cage, and it occupies a greater volume when the ribs are more perpendicular to the spinal column, and we raise the volume even more. Bring in air under the greater pressure difference, greater pressure gradient. During expiration, we will then hasten the removal of air from the lungs by using the internal intercostal muscles to pull the rib cage downward, and that collapses the rib arrangements against the spinal column and reduces the volume even more, higher pressure gradient, and we expire air more vigorously. There are other muscles that actually assist with inspiration, expiration during exercise. You can look into that if you're interested. It's a wonderful topic in exercise physiology. This diagram is just showing us graphically what's happening to the pressure inside the lungs, the intrapulmonary pressure as we inspire and expire, right? So this is the pressure inside the lungs. As we inspire, we increase the volume, which causes the pressure to go down, and air rushes in. We can see what's happening to the volume. Air is coming in. We have volume in liters entering the lungs, and then when we reach full excuse me, inspiration, then we raise the pressure by decreasing the volume. We let the diaphragm relax, the alveoli begin to recoil, the volume goes down, pressure goes up, and air leaves by passive flow from higher to lower pressure. There are three variables that we want to mention and describe briefly that affect the ability to move that air in and out of the lungs. How well can we ventilate the lungs? One is the resistance to flow of air in those pipes. We saw that there's a relationship, an inverse relationship between diameter of blood vessels and resistance to flow, and the same holds true for the airways. The more narrow the airways, the greater the resistance of airflow, resistance to airflow. Surface tension is a force that we're going to talk about and introduce that opposes expanding the alveoli. So that's another force that can affect ventilation. And lung compliance is the ease with which we can expand the lungs. If the lungs are very compliant, it's easy to expand them, and we can ventilate easily. If they're very stiff, there's low compliance. So what about resistance? This interesting graph shows you the resistance on the y-axis to airflow, opposition to airflow, and on the x-axis is showing you the number of branchings of the bronchi. So there's around 23 branches down to the terminal bronchioles. It turns out that the intermediate sized bronchi have the greatest resistance. Just like the arterioles have the greatest resistance to blood flow, and therefore we manage the overall peripheral resistance by vasoconstriction and vasodilation of arterioles. While in the lungs, the most resistive bronchi are the intermediate sized bronchi, and if we bronchodilate and constrict those, that impacts the overall resistance to airflow. If we add some histamine to the system, that'll cause bronchoconstriction, increasing the resistance to airflow, and we'll have an inhibition of ventilation, a tougher time ventilating. This is Ohm's law right here. Flow is driven by a difference in pressure. So the greater the difference in pressure from inside to outside of the lungs, the greater the flow rate, but it's opposed by resistance, which is essentially the relationship between flow and the diameter of the pipes. And so the greater the resistance, the lower the flow. And this is the same formula we use to define the flow and the resistance, the driving force and resistance to flow in the cardiovascular system, Ohm's law. So if we have some inflammation and throw some histamine at that situation, bronchoconstriction will happen, right? If we have an allergic reaction or asthmas and hypersensitivity just to irritation in the lungs, we will have difficulty with ventilation. We'll use a bronchodilator, a chemical that causes relaxation of the smooth muscle in the airways. The most commonly used chemical for moderate asthma, for example, is an inhaler that has aerosolized albuterol, which is a beta-2 agonist, which causes bronchodilation. But in emergency situations, if we have systemic anaphylaxis, we may use an EpiPen, stab it right into the body and get some pure epinephrine into the blood, and that will cause bronchodilation and help get the breathing going, help get the ventilation more easy. Here's just a little diagram showing you all the different branchings of the bronchi and reminding you that the rings of cartilage and all those airways are C rings, not circular, not complete rings, and so that we can contract smooth muscle and reduce the diameter of the bronchi, and those intermediate bronchi will cause the biggest increase in resistance. Surface tension. It's kind of a strange concept if you haven't thought about it before because it seems unlikely. But it turns out that water molecules are polar. They have electric charge to them, and different parts of a water molecule have negative charge and positive charges, not formal charges, but they are electrostatically interactive. So water molecules cling together by these electrostatic interactions. They're like little magnets, and if you have trillions of these little magnets and you try to expand the alveoli, you're essentially pulling apart all those little magnets. It takes work. They exert a force, an attractive force on one another, and that's called surface tension. The alveoli do not want to expand. The water molecules want to pull them downward. They add to the sort of elastic recoil properties. In order to help overcome that surface tension effect, we have some surfactant dissolved in the water on the surface of the alveoli, and it helps overcome the attractive forces between the water molecules, making it easier to expand the alveoli. It also prevents the collapse of small alveoli into larger ones. Turns out if you had two dissimilar sized alveoli and connected them by a tube, the smaller alveolus would just collapse into the larger alveolus. But that's a subject of essentially biophysics, which you can also look up if you're interested. A very cool principle. Well, surfactant overcomes that tendency so that all the alveoli don't have to be identical in size to prevent them from collapsing into each other. So anyway, surfactant makes it easier to breathe or ventilate. An interesting caveat is that premature infants don't have enough surfactant production. Their type 2 alveolar cells, those ones that were drawn in green in that diagram last time, don't secrete surfactant yet. They weren't meant to be breathing yet, right? They're still supposed to be in the womb, and so they can't overcome that surface tension. They can't ventilate on their own. They don't have the physical ability to draw air into the lungs, and so we need to assist them either by adding some surfactant to the fluid in their lungs or by putting them on a ventilator, which will force air into the lungs from outside using an air pump, which it turns out is actually unhealthy and detrimental to the health of the lungs. Infant respiratory distress syndrome is what it's called if a premature infant typically has trouble breathing because of this insufficient amount of surfactant. That may be connected to sudden infant discontinuation of breathing. There's a mysterious syndrome in which on very, very, very rare cases, infants just stop breathing. And I think that infants that are earlier term, preterm infants are more likely to experience that sudden lack of ventilation and they die. Lung compliance, the third variable that we'll talk about that affects ventilation, it's the ease with which the lungs can be expanded. The more compliant, the easier it is to expand. For a given difference in pressure, air pressure, the more compliant the lungs, the greater the volume change will be. So if the lungs are very compliant, they're healthy, elastic, young lungs typically. There's a caveat to that too. If we have reduced surfactant, that decreases the compliance, makes it harder to expand the lungs. If we have fibrosis, if there's a disease in which scarring is taking place in the lungs, chronic inflammation, maybe because an irritant, an industrial irritant is getting into the lungs on a daily basis at work, it could lead to fibrosis and scarring of the lungs. The lungs are less compliant and it's harder to get air in. Ossification, the costal cartilages will slowly be converted to bone with age. The rib cage becomes more and more stiff, less and less compliant with age, and it becomes more and more difficult to ventilate. The depth to which one can inspire air or ventilate becomes reduced with age unless there's a vigorous attempt to practice, to exercise throughout late adult life. Spirometry is the practice of measuring the lung volumes and capacities as a subject inspires air and it expires air. This little light blue band represents the volume of air coming into and out of the lungs during resting or relaxed breathing. As you just sitting here right now watching this session, you're breathing in and out about a half a liter probably of air each time. That's called the tidal volume. So that's sort of like the middle of the range, the tidal volume. And then as you know, when you exercise, you can breathe much more deeply, or for a number of reasons. You can inspire a much greater volume of air. So after a tidal inspiration, if you then decide to inspire all the remaining air you can possibly voluntarily admit into your lungs, that's called the inspiratory reserve volume. So in this instance, there's about 3.1 liters of additional air that can be inspired into the lungs, the inspiratory reserve volume. Also, if you expire a tidal expiration, right, just relax breathing, and right before an inspired breath, you decide to force out all the rest of the air you can push out of your lungs voluntarily. There's a limit, and that additional air you can expire is called the expiratory reserve volume. Again, in this case, about 1.2 liters. There's a couple of neat things to mention about this graph. One is that you cannot expire all of the air out of the lungs. No matter how hard you try, there's always about a liter of air left in your lungs. It's called the residual volume. You can't get that out of there. It's good that you can't, because if you got all the air out of there, all the alveoli, the lungs would collapse, and you would be unable to reinflate your lungs. Think of how hard it is to first blow up a balloon when it's in that most relaxed state, when you first pull it out of the bag, and then once you start getting some air and it suddenly expands much more easily, and you can change the volume, add some air, let some air out. That's how your alveoli are. We never want them to completely empty out. We want to keep them partially inflated, and it's relatively easy, especially with the presence of surfactant, to add some volume and let them recoil and add some volume. So we keep residual volume in the lungs all the time. The rib cage will not collapse any farther down, and we can't let the rest of the air out. We don't have the ability to do it. Okay, so another thing that I want to introduce a term called the vital capacity. That's the total volume of air that you can control and voluntarily. In other words, if you inspire all the air you can possibly inspire, a maximal inspiration, and then you expire all the air you can possibly push out, that total volume from maximal inspiration to maximal expiration is called the vital capacity. It's the sum of inspiratory reserve volume plus tidal volume plus expiratory reserve volume. And we'll use that in a diagnostic evaluation of lung function. Because with obstructive disease, an obstructive pulmonary disease is one that's characterized by an inability or inefficiency in getting the air out. It's very hard to expire air. When you have bronchitis and emphysema, a relatively common condition, unfortunately, called COPD, it's the endpoint of a life of smoking cigarettes. The condition of your lungs will be such that you have degradation of the alveoli and the structures of your lung tissues, and you have chronic inflammation called bronchitis, with lots of extra mucus being produced and narrowing of the airways, and it makes it very hard to expire air. The harder you try to breathe out air, the more air becomes trapped in the alveoli and alveolar ducts, and so you can't breathe out very well. And that will affect the performance of your pulmonary system, and we'll look at that again in a bit. Another class of pulmonary disorders are called restrictive disorders or restrictive diseases, and that's what I was talking about earlier. If you have a chronic inflammation, exposure to some irritant, for example, occupational exposure, eventually some scarring will reach the point where you can no longer inspire the normal amount of air into your lungs. The volume you can inspire will become greatly reduced. In other words, the inspiratory reserve volume will be way lower than it should be, and so you won't have your vital capacity. That sum of these volumes will be greatly reduced. Can't get the air in. So we can evaluate those things by measuring the vital capacity and measuring the rate at which you can expire air. So the forced vital capacity is just the name of the volume you expire in a test in which you inspire all the air you can inspire, and then you force out all of the volume and measure it on its way out, and we call that result the forced vital capacity. And the forced expiratory volume We're going to do that same test again, only inspire all the air you can inspire into your lungs and then force it out at the greatest possible rate. Vigorously expire air. We're going to watch and see how much air comes out at each second. It's the flow rate essentially, but we're going to look and see how much of the vital capacity can we expire in 1 second. That's called the FEV1, or forced expiratory volume in 1 second. And it's going to be greatly reduced with obstructive disease. We can't get the air out. And so in our lab exercise of the respiratory system, we would actually measure the FEV1 and the vital capacity and figure out the percent. It should be around 70% to 80% of the vital capacity should be expired in 1 second during the maximal expiration force. We can quantify the ventilation of the pulmonary system in the simplest terms by multiplying the tidal volume, the amount of volume that's being inspired and expired at rest, times the frequency. How many breaths per minute are we producing or undertaking, and how much volume is in each breath? Multiply them together, now we have the liters per minute of ventilation. There's a problem with that in terms of the usefulness of that metric, and that's because of this interesting property of your pulmonary system. When you inspire air, some of that air goes down into the alveoli, the respiratory zone of your lungs, and there's gas exchange, but some of that air stays in the trachea and the bronchi and the bronchioles. It never actually does much of anything. When you expire, then all that air goes right back out. When you finish expiring, the trachea, the bronchi and bronchioles are all still full of air that has already had oxygen extracted from it. It's not fresh air. It doesn't have the normal amount of oxygen that would be coming in from the room. And when you go to inspire again, the first thing that happens is all that so-called dead space air goes right back down from those airway spaces down into the alveoli. Not much help. It's not good fresh air. Then, after that air goes down, fresh air from outside then enters the airways and goes down into the alveoli and mixes with that dead space air. That volume occupied by all those airways is called the anatomical dead space, about 150 milliliters. So again, when you first begin to inspire, 150 mils of stale old, already exhausted air is going back down into the alveoli, and then it's being followed by fresh air. So we may want to have a way of estimating how much fresh air is actually going down into the alveoli each time as we're breathing. It's called the alveolar ventilation rate, much more informative physiologically. We figure it out exactly the same way with a slight correction. We just say that the alveolar ventilation rate, the fresh air going in the alveoli, is the frequency of breaths per minute times the tidal volume minus the dead space, because that's not doing us any good. And now we can say, okay, every bit of air that's additional to the dead space that we're bringing in is going to be good fresh air rich in oxygen and help the body. So shallow breathing, in which a lot of the volume that we're inspiring each time is really just dead space, isn't very efficient or effective, whereas deep breathing, where we're bringing mostly fresh air in on top of that dead space air volume, is much more effective at getting oxygen into the blood. Here's an interesting revealing kind of look at the calculations. 3 different situations in which ventilation is taking place, and in each case the minute ventilation, the frequency times the tidal volume, is identical. In each case it's 10 liters per minute, or 10,000 milliliters per minute. Let's look at the alveolar ventilation rate in each case. If the tidal volume is 500 mils, 500 mils is how much you're breathing in and out each time at rest, and the dead space volume is 150 mils, the alveolar ventilation rate is 7 liters per minute, not 10, because a lot of the time we're breathing in that dead space air. So 7 liters per minute of good, fresh air is getting down to the alveoli. If we breathe a little deeper, if we increase the tidal volume to 1,000 mils, a liter per breath, but we slow down the frequency so that the minute ventilation is still 10,000 mils per minute, 10 liters per minute. Now we have a greater alveolar ventilation rate. We've brought a larger amount of fresh air into the alveoli, same minute ventilation, so deeper breathing has been more effective. If we're breathing more shallowly than usual, and we have only a 250 mil tidal volume, then even though our minute ventilation is the same, 10 liters per minute, we only have 4,000 or 4 milliliters, I should say 4,000 milliliters of fresh air per minute getting down into the alveoli. So pretty interesting quantification of alveolar ventilation rate relative to minute ventilation. Okay, so next time we'll start up and talk about the actual exchange of gases and all about getting gases into the blood from the alveoli, circulating it to the tissues and getting the oxygen back off the hemoglobin into the tissues and getting the CO2 out of the tissues and back to the lungs and so forth. So that'll be a subject of our next meeting. So join me for part 3, I guess it will be, of the respiratory system.